Welcome back students to the video lecture series. I am Adil Mansoori from Civil Engineering Department of LJ Institute of Engineering and Technology. So my dear students, in this video we will discuss regarding a device known as mixing device. Okay, so as we all know that in sedimentation tank certain particles which are lighter in weight, right, and which have density of less than that of water, then they usually try to float in water or they remain in suspension, right? So for them to get settled in the sedimentation tank or in the clarifier, what we do is we usually add coagulant, right? So these mixing devices are usually adopted for proper mixing of coagulant with the water. Okay, so let us start. So as I said that mixing devices are of two types. Okay, first one is known as mixing device with baffle walls. Okay, and another is known as mixing device with mechanical devices. Okay, students, so let us start with the first one, that is known as the mechanical devices with baffle walls. Okay, so you can see over here that this is the plan of an underground tank, right? So here this is the inlet. Okay, the water will enter into the basin, okay, through inlet. Now you can see that these are the baffle walls. Okay, right, and water will enter through this, it will collide with this wall, right, so that effective mixing will be done, right, because of the turbulence created. Okay, so when the water will enter into this basin, right, baffle walls will lower the velocity of water, right, and it will create the turbulence, and hence effective mixing of coagulant will be achieved. Okay, clear? So after coming out, it will be removed through the outlet. Okay, so this is the baffle walls. Clear? Let's see a second type of mixing device, which is known as the mixing device with mechanical devices. This is also known as rapid mixing device. Okay, it is also known as rapid mixing device or rapid mixer. Okay, so as you can see, this is the inlet. Okay, then here this is again a baffle wall, right? Then this is known as the impeller. Okay, so on impeller there are the blades. Okay, or you can say there are paddles, right, and this is the motor, right? So motor is connected to the driving shaft. Okay, okay, and this is a pipe for adding chemical. So we can say that this is chemical feeding. Okay, fine. And after proper mixing, it will be removed through outlet. Understand, students? Clear? Okay, students. So in rapid mixing devices, intensity of mixing is dependent on a term known as mean velocity gradient. Okay, what it is known as? Mean velocity gradient. Okay, it is denoted by capital G. Okay, so mean velocity gradient is the change in velocity per unit distance normal to the section. Okay, so it is the change in velocity per unit distance normal to the section, right? So unit of G, what shall be the unit of G? Change in velocity. So unit of velocity is meter per second, agree, per unit distance, right? So divided by m. So unit of G will be second inverse, agree. Now we have to find out this mean velocity gradient. We have to find out the power, right? So for that we are given G equals to P upon mu into V, right? Where P will be equals to power in watt, right? Mu will be equals to absolute viscosity, right? And its value will be equals to 1.0087 into 10 to the power minus 3 Newton second per meter square at 20 degree centigrade. Okay, and V will be equals to volume of water in meter cube. Okay, so this is a relation from which if any of the three quantities are known, we can find out the fourth quantity, right? So next is finding out power, right? So power will be found out from the equation 1 by 2 CD EP rho into VRQ. Okay, so what is CD? CD is known as coefficient of drag. Okay, EP will be known as area of paddle or blades, you can say. Rho will be density of water, right? And last, VR will be relative velocity of paddles with respect to that of the water. Okay, now there is another relation which is known as VR equals to 3 by 4 of VT. So in case we are not given VR, then we have to assume VT, and from this relation we have to find out VR, right? So VT here will be tangential velocity, right? So once again, this is a mixing device with rotor or impeller, right? and this is dependent on g, that is mean velocity gradient, right? So mean velocity gradient can be found out by this equation, that is under root of p by mu into v, where p will be power in watts, mu will be absolute viscosity, and v will be volume in meter cube, right? Then there is another equation, p equals to 1 by 2 cd ap rho into vr cube, right? And vr is the relative velocity of paddles with respect to water, right? And if it is not given in the data, then we have to assume vt, that is tangential velocity, and from there we can find out vr. Okay, so this is how the mixing devices are. So let us move ahead and find out how mixing devices design. So next is design criteria of flash mixture. Design criteria of flash mixer. Okay, so first criteria, as usual, detention time, right? So this is usually in between 30 to 60 seconds, and ideal value you can go for is 30 seconds. So if they have not given any kind of data, then you can assume 30 seconds and move on. Okay, then second one, ratio of height to diameter of tank. Okay, so this is usually 1.1, sorry, 1:1 to 3:1. You can go for 1.5:1. Okay, then ratio of impeller dia to tank dia, right? So this is usually 0.2:1 to 0.4:1. You can go for 0.4:1. Okay, next, velocity gradient, that is mean velocity gradient, that is nothing but g, right? So this value should be greater than 300 per second. What you can go for is 600 per second. Okay, then fifth one, impeller speed, right? This should be greater than 100 rpm, right? What you can go for is 120 rpm, right? Then next, tangential velocity, vt should be greater than 3 meter per second. Okay, and we have known one relation, that is vr equals to 3 by 4 of vt. Okay, so these are the design consideration or design criteria for flash mixture, right? So we will now solve the design example of flash mixture. Okay, so let us start with the numerical. Numerical says, design a flash mixture for a discharge of 270 meter cube per hour and assume suitable data, right? Now we are not given anything, so let's start with the assumptions, right? So first thing we will do is the assumptions. First assumption, detention time. How much shall we take? 30 seconds. Okay, then second one, velocity gradient, that is G, right? How much? 600 per second. Then third, speed of impeller, speed of impeller will go for 120 rpm, right? Then ratio of height to diameter, ratio of height to diameter, how much we will take? 1.5 is to 1. And last, ratio of impeller to tank dia, so that is equals to 0.4 is to 1, right? So these should be the first assumptions, right? Now let us move ahead. Let's start with the step number 1. So step number 1 includes determination of dimensions of tank. Right? So first thing, volume of tank, that will be equals to discharge into detention time, right? So this will be equals to 270 meter cube per hour. So multiplied by 60, it will give us in 270 meter cube per second, right? So that's why we have converted into second, and time that we have taken is 30 seconds. So this comes out to be equals to 2.25 meter cube, right? Next, volume equals to area into depth, agree? Now this is a circular tank, so area will be equals to pi by 4 d square, and we can assume depth equals to 1.5 times diameter. Okay, so volume we have got 2.5, therefore from here we can get diameter equals to 1.25 meter, right? Or we can approximately say that provide diameter equals to 1.25 meter. Okay, so once we have got the diameter, we can find out depth of tank, that is equals to 1.5 into diameter, that is 1.5 into 1.25, that is equals to 1.875 meter. Okay, clear? Next, provide freeboard. .2 meter. Okay, so therefore what will be the total depth? Total depth will be 1.875 plus 0.2, and that will be equals to 2.075 meter. Okay, so we have found out that tank dimensions will have diameter equals to 2.075 meter, sorry, diameter will be equals to 1.25 meter, and depth will be equals to 2.075 meter. So this is step 1, which will include determination of the dimension of tank. Okay, so let us start with the next step, that is step 2, where we will be finding out power requirement. Right? So as we all know, this equation, that is G equals to P by mu into V, right? Therefore can I say P equals to G square into mu into V, right? we have assumed G value as 600, 1.0087 into 10 to the power minus 3 will be mu into 2.25 will be the volume. So this power comes out to be equals to 817.047 watts. Okay, right? So this is step number 2. Now let's go for step number 3. Step 3, dimensions of impeller and blade. Right? So here, diameter of impeller to tank dia we have assumed as 0.4, right? So diameter of impeller will be 0.4 into tank dia, that will be equals to 0.4 into 1.25, that will be equals to 0.5 meter. Agree? So that will be the diameter of the impeller. Now velocity at tip of the impeller, or you can say tangential velocity. Tangential velocity will be 2 pi rn in meter per minute, right? So therefore we can say Vt will be equals to 2 pi rn, that is equals to 2 pi. Now r will be equals to 0.5 by 2, diameter by 2, right? And n 120, right? But since it is in minute, you will divide by 60. Okay, so this will be equals to 3.14 meter per second. Okay, right? Because we have assumed n equals to 120 rpm, that is rotations per minute, right? So for that case, if it is in rotations per minute, we will consider in second. Okay, now as per the criteria, this velocity should be greater than 3. So is it permissible? Yes, therefore it is okay, right? So velocity at tip of the impeller or tangential velocity 2 pi rn meter per minute, 2 pi rn, and it is 120 rotations per minute, right? But since we want velocity in meter per second, we are dividing it with the 60, right? That is number of rotations per second, right? So this comes out to be equals to 3.14 meter per second, right? And this value should be greater than 3. Clear? Now for area of blades or pedals, P will be equals to 1 by 2 CD AP rho into VRQ, right? We know this equation. So VR we don't have, so we will take as 3 pi 4 of VT, that is 3 pi 4 of 3.14, and this comes out to be equal to 2.36 meter per second, right? So we have got VR, density we know 1000, area of pedal we need to find out. CD for flat plates it is always 1.8. okay, so CD for flat blades or plates, it is always equals to 1.8. So we have CD as well. Power we have found out in the previous step, right? So therefore, let us say 817.047, that is power, equals to 1 by 2. CD, in place of CD I'll take 1.8. AP we need to find out. Density 1000, right? And VR, that is equals to 2.36. So therefore AP will be equals to 0.069 meter square, right? So area of paddles will be 0.069 meter square total. Okay, now you can provide any number of paddles or blades, right? I am providing 6 numbers, so let us provide 6 numbers of paddles, right? Therefore area of each paddle will be equals to 0.069 divided by 6. Okay, so this will be equals to approximately 0.012 meter square, right? So dimensions will be rectangular, therefore provide blades of size 0.10 by 0.12 meter. Okay, that is equals to 10 centimeter by 12 centimeter. Okay, so here we are completing the dimensions of the blades as well. Okay, so let's go through quickly. So we have assumed detention time, right? That is 30 seconds. Mean velocity gradient g 600 per second. Speed of impeller 120 rpm. Ratio of height to diameter 1.5:1, and ratio of impeller to tank diameter 0.4:1. Right. So first step, determination of tank dimension. That is, from discharge we will find out the volume, right? And from volume we will assume the depth 1.5d, right? That is 1.5 times the diameter, right? And from that we will get depth and diameter. Then provide total depth and total dimensions. Step 2, power requirement. So this is the equation for power, and we found out power as 817.047 watts. Next, diameter of impellers and blades. So we had taken this relation. So from that we found out total diameter of impeller 0.5 meter, right? Then tangential velocity can be found out with this equation, that is 2 pi rn, and n is number of rotations per minute, right? But since we want tangential velocity in second, we divided it with 60, right? And this velocity, whatever the velocity comes from this equation, should be greater than 3. Then to find out area of blades, we need to follow this equation. P equals to 1 by 2 CD AP rho VR cube, right? Everything is there. So we ultimately found out area of blade size to be 10 by 12 centimeter. Clear?